Well, I'm going to start the class now. So what we'll do today is to talk about recursion again. Remember we talked about recursion last Thursday. Are there any questions about subroutines, from last Thursday? How to invoke a subroutine and what to do at the end of a subroutine so you can continue execution after the end of the subroutine.
Question about home.
Yep, go ahead.
Okay, so the whole deal is infinite loops, I guess. So that was basically the whole of the homework. Well, what description should we give for the infinite loop? Because I know exactly where it starts.
Okay.
I don't know how to describe it.
You can describe it by saying, you can observe that, all the variables involved in the until condition do not change over 2 iterations. So that's a guarantee that it won't change again in the 3rd iteration because the transition from the first to the 2nd iteration is going to be the same as from the 2nd to the 3rd transition. So from that, you can basically deduce that it will continue on because the condition is not going to change. The exit condition will not be true because it's not going to change. All right, so what we'll do today is to continue our discussion with subroutines. And today we'll kind of take a look at recursion again, and basically look at how recursion can be useful practically. And I'm going to use factorial, which is an overused example of recursion. To illustrate recursion is to use factorial. But in order to use factorial, I don't want to just talk about factorial because if I just define factorial as this, you guys would say, well, that's kind of boring. Why would I want to care about factorial? In this class, I'm pretty sure we talked about factorial already. With the pizza delivery example and the UPS truck thing. Okay. Yeah. So just to quickly go through that example, you have a pizza shop here, and then you have just kind of random spots that you have to deliver the pizza to. So in this case, it's no clear, easy way to figure out which way to traverse A, B, C, and D and back to the shop is going to be the least expensive. So the way you do it is you basically figure out all possible permutations of A, B, C, D. So it will be A, B, C, D, A, B, D, C, and then A, C, D, B, and then A, C, B, D, and so on. And then you compute the actual time that it takes for each permutation to do the traversal, and then you figure out which one is the fastest, and you pick that. It's an optimization problem. Okay. So that's actually an application of factorial because with 4 possible destinations or 4 points that you have to traverse, you have 4 factorial ways or permutations with these arrangements. So you have 24 possible ways to arrange A, B, C, D, and that's the number of routes that you have to consider. That's the first time we encountered the concept of factorial, which is 4 times 3 times 2 times 1. So what we'll do today is to continue with some of the applications of factorial first, and then we'll go back to algorithms and subroutines to take a look at how do we compute n factorial using recursion and how to do it without using recursion. Okay. Are there any questions before we proceed to talk about how factorial can be useful on a pretty much daily basis? How many people have taken statistics? Okay. And in your statistics class, do they talk about factorial? Yeah, because it's one of the more important concepts in in statistics. So for those of you who have taken statistics, what we're going to talk about next may be kind of slightly boring because they might have talked about this already. So what we'll do is we'll go to the Lotto website, and what we want to do is to look at well, I did one for the other class. I did Powerball with the other class. So what we'll do today with this class is to look at another game. Let's say Mega Millions. Okay. And by the way, I have no idea how these games are played, so I'm going to have to read the rules to figure out when is it worthwhile to play this game. Okay, that's basically the objective here. So what we want to do is to look up the rules, which is under how to play. All right. So step 2 is basically the instruction of the game itself. It will give us all the information that we need to do some calculations. So in this case, we have to pick 5 lucky numbers from 1 to 75 and one mega number from 1 to 15 on a mega million place slip. Okay, so this is what we will do. And what I want to do is to figure out, okay, what are my chances of winning the top prize for Mega Million as the lotto game. Okay, do you think that might be useful math? I mean it seems useful. the result may surprise you. Okay, I'm hoping that it won't, but to some people that might be surprising. All right. So the first thing we have to do is to figure out how many combinations of 5. Okay, how many combinations do we have when we draw 5 numbers from 1 to 75? That's the question. Okay, so at this point we have to talk about the differences between a permutation as opposed to a combination. Okay, so let's say we have 4 items. Okay, so we start with 4 items, which is A, B, C, D, and let's say we have to pick 2. So we pick 2 out of 4 items. The question is, how many permutations do we have? The first question is, how many permutations do we have when you have to pick 2 out of 4 possible items? The answer is, you have 4 choices for the first item, because I have not chosen anything yet for the first item. But once you have chosen the first item, you will have only 3 left for your second item. So together, you have 12 possible permutations. Are we doing okay so far with that? Okay. Now, when you talk about combination, the order is not important. When we talk about permutations, AB is one permutation, BA is another permutation, BC is one permutation, CB is another permutation, and so on. But when we talk about combinations, so this is permutations, when we talk about combinations, the ordering does not matter. Okay, AB is considered the same as BA, BC is considered the same as CB. So the question is, well, what about combinations? How many combinations do we have? One way to figure out the number of combinations is to look at the number of permutations, and then you say, well, for each possible combination, how many permutations do we have? In other words, if I just look at picking A and picking B, how many different ways do I have to rearrange A and B so that they come out as different permutations? Well, in that case, it is 2 choices for the first one, and then 1 choice for the second one. So it's 2 times 1. So in this case, there are 6 unique combinations when you have to choose 2 items out of 4. Okay, does that make any sense to you? Well, let's figure out what those 6 are, just to be sure. Okay, so we have A, B, C, D, and we are now looking at combinations where ordering does not matter. Okay, so with 4 items, you can pick A, and then A combined with B, A can combine with C, A can combine with D. Is that okay? Mm-hmm. And then the second item, you can pick B, but I don't want to consider BA anymore because BA and AB are considered the same. So with B, I can pick C to combine with it. I can pick D to combine with it. And then the last one is to look at C. And I don't want to look at CA because AC and CA are considered the same as a combination. I don't want to look at BC because the CB and BC are considered the same. So the only combination I have not considered yet at this point is CD together. So we have 1, 2, 3, 4, 5, 6 combinations, but we do have 12 permutations because there are 2 permutations per combination in this case. Are we doing okay so far with with the concept of permutation as opposed to combination? Okay. When you play lotto, are we dealing with combinations or are we dealing with permutations?
Combinations.
We're dealing with combinations. Okay. The ordering of the lucky numbers, they do not matter. Okay. So the question now is, how many combinations do we have when we have 1 to 75 to select from as my lucky numbers, and then 1 mega number from 1 to 15, which I think can overlap with the first numbers that you have chosen. Okay. So that's the question. All right. So what we'll do is we'll take a look at this problem and say, okay, 75 to choose from. So the first number that you choose can be out of 75, But once you have chosen the first number, you only have 74 to choose from, and then after they have 73, and then 72,
17 million.
and 71. Okay.
That's it.
Well, the website actually shows the number, but I want to go through the whole calculation and then use that to double check that my calculation is not off. Okay, so we have 75 times 74 times 73 times 71 times 71, and what are these? Are these combinations, or are these combinations, or are they permutations? They're permutations. Okay, because I have 75 numbers as my first choice, I have 74 as my second choice. But you know what? I can flip the order, right? You know, I can choose A instead of B first, and then choose B first instead of A. It will be counted as two separate items if I count it this way. So what I need to do is to divide this number by the number of ways, or the number of permutations with 5 unique items. Well, I already know that with 5 unique items, there are 120 ways to arrange them, because I have, out of the 5 items, I have 5 choices for the first one, 4 choices for the second one, 3 choices for the third one, and only 1 choice for the last one. So this will give me the number of combinations for the lucky number, and then on top of this, we can multiply the 15 as my mega number, and that's the total number of possible tickets they can possibly purchase, or this is the number of unique tickets they can buy for this particular lotto game. Now, what does it have anything to do with Factorial? Well, it has a lot to do with Factorial, because first of all, let's take a look at this product first. This product does not look entirely like a Factorial, but it can be computed using Factorial. Now, how do we compute this number using Factorial? Well, if you look at the top part here, we can say, well, let's look at this as 75 times 74 times 73, okay, times 72. Oops, cursor keys. Ah. Okay, numlock. 72 times. I cannot use the numpad. 71 times 70 times 69 times blah blah blah, down to 1. Okay, but that's not the number that we want. But on the second row, or as the denominator, we can also say, well, let's divide this number by 70 times 69 times blah blah blah, down to 1. Is everybody convinced that this math should work out? The top is the product of 75 all the way down to 1. The bottom one, or the numerator, is 75 times everything, the product of 75, 74 all the way down to 1. And then the denominator is 70 times 69 times everything down to 1.
75 factorial divided by 70 factorial.
Yep. But does it, first of all, does it come up with this number that I actually want?
Yeah.
Yep. Because it cancels out.
Cuts off the tail essentially.
Yep. So it becomes, so you can look at this as 75 factorial divided by 70 factorial, okay? And what about this part here? What does that look like to you?
5 factorial.
That's 5 factorial, exactly. So the entire number, the number of unique tickets for this particular lotto game is 75 factorial divided by 70 factorial divided by 5 factorial. And then you have to multiply 15 because that is independent to the first 5 numbers that you have chosen. So now we want to take a look at this number and figure out, okay, but what exactly is that number? I know on the website they already published the number, because that is required by law, that they have to let people know what the chances are.
Chances, how good the chances that they won't succeed are.
Somebody has to.
Well, by law, I think they have to do that. So we have the factorial of 75 divided by the factorial of 70 divided by the factorial of 5, and then this whole thing times 15. So it adds up to, let me format the cells to just general numbers. 258 million possible 259 259 billion unique tickets. Okay.
So there's a chance.
Well, there's a chance, yes.
As long as there's a chance.
According to quantum physics, if you keep banging your head, on the wall,
Oh, yeah.
you may pass through eventually. There's a chance too. Quantum physics.
I was sure about that.
You have to like quantum physics. It's like, okay.
Yeah.
So that's a possibility there.
So there's a chance.
Yep.
You may
All
die
right.
of old age before
Okay.
that happens, so.
So let's double check first, okay? Because on the website, they should also indicate that number. Okay. So a total match with all 5 and 5 and the mega number. Yep, that's exactly the number that we have here. Okay. And what is the cost of each lotto ticket for this particular game?
$1.
Is it $1? Okay.
Usually something like that.
So if it is $1, that means the payoff. In order for this to break even, the payout money has to be $259 million. To
taxes.
well, let's factor those things in. Okay,
Let's
so
say you escape with the money and the government doesn't catch you.
so let's. You have to go to another country, that can hide you.
Yeah.
But that much money can probably hide you pretty well in certain countries. In fact, they can arrange a assassination and say that, oh, you know what, Tak is dead now, and here's the charred body.
Couldn't find the money though.
Yep. Strange.
And then
Okay, so once you factor out taxes, because I think at that number, the tax is at least 50%, combining
Yeah, it's
state
close.
and federal tax. So you have to double the amount of money to make it worthwhile. And then after that, you have to look at this and say, if the payout money is close to $259 billion, how many people or how many tickets will be sold? Okay, because the assumption so far is you are the only player.
oh my god.
You buy one ticket, okay, and you have a chance out of 259 million, 1 out of 259 million, that you will win, and you pay the federal taxes and the state taxes. So you need $500,000 as the payout money to just break even, okay. But now you have to look at historically speaking, when the payout money is at least 200 and something million dollars, how many tickets typically will be sold as a result? What do you think? Hmm? I would say it's more than that number.
Yeah.
Okay, they actually sell more numbers than there are unique, combinations. In fact, it's probably a lot more than just that number. I would guesstimate it's at least twice that number. Okay, so that means the chances of someone having the same ticket as you is close to 1. Okay, so that means you have to share that money with that other person with an identical ticket. So now you have to look at this number and say, well, better be safe and double that number. So now you're talking about $1 billion. Okay, so that means when the prize money or the payout is $1 million, then based on this calculation, you may break even to buy a ticket. Some people can just look at these math here and go like, I don't really understand the math at all, but I feel lucky today. I'm going to buy my ticket.
Today's the day.
Yep.
Today's the day I win.
And for those people, there's no argument that can work, right? I mean, because it's all based on belief in that case. I just look at the numbers and say, okay, what are my chances? Yep.
I hit $500 on a scratcher just on my Friday.
Okay.
So I probably broke even overall.
So you purchased 500 tickets altogether.
No, well, I just
A couple of cost $2.
Yeah.
Well, plus, once you win, big prize monies, you might discover long lost, cousins and relatives that you have never known before.
That haven't even been in the States for a few generations.
It's like, hey,
Out of country cousins is like, wow.
Did you know that the Prince of Zimbabwe wants to hold on to your money for you? An email.
I might end up with some Irish, cousins. All right. Well, that's one practical use of factorial, because it's all based on combinations and permutations, and behind combinations and permutations, factorial is the basic operator that is useful. Are there any questions about this math here? And by the way, where does that money go? I mean, because on the average, the lotto has to be making money instead of losing money. So who's getting all that money?
Lotto commission.
Actually, it's me and other people in the education business in California. Yep, that's actually required by law. I mean, that money has to go to education. It's not going into general funding. It's going into education.
There's a silver lining.
So you guys should go play more lotto.
And when you guys will win the super lotto.
No, I really think the state should find other ways to make money and to fund education. Because this kind of goes against education. The more educated people are, the less likely they should play lotto. I would think.
Well, the ones who need it most are the ones who are essentially funding it.
That's one way to look at it. Yep. Without knowing it.
Without knowing.
Correct. That is interesting. That is an interesting thing. It's like, I'm funding education, but I'm not getting the education that I need. Right.
Well, I don't think there's any regulations on where I know it goes to education, but there's not any regulations on what exactly it goes to. So, like, it doesn't benefit where it should benefit the most.
So you're saying that I'm not benefiting from all this?
Not as much as,
No,
maybe
you
not as
are,
much as you
but-
should.
I don't
Right.
know, I guess I have 4 kids and I see where improvements can be done, and if there's that much money going in education, where's the money at?
Administration.
Yeah, exactly.
Yep. Administration and contractors.
Superintendents.
And contractors. Okay, don't forget the contractors because they're not even state employees, so they are just the money is flowing out.
Oh, I know
Yep.
about contractors. My husband works for the state, so.
Right. Yep. All right. So that gives you a sense of probabilities and stuff like that. If you analyze most games that casinos do, most of those can be analyzed using combinations and permutations
But they don't like
and
it when you do
statistics
that.
in general.
Yeah.
Well-
They frown upon it heavily.
Oh, they kick you out. They don't frown. They just kick you
Maybe
out.
they'll- Sometimes I think they bring up lawsuits, but
So is blackjack your best odds?
Hmm?
That playing games, is blackjack your best odds?
Yeah, but from the previous class, they changed the way the blackjack is done. In the casino, it
Yeah.
used to be just playing decks of cards, and then people started to count. And now I think they take the cards back and reshuffle and
Yeah, they just put it in this thing that just randomly shuffles it all the time. So.
Yep.
The higher amount that you bet, they use more decks, so your chances of winning are a lot less.
Yeah,
But if you go to like 100,
Mhm.
or they use like 2 decks,
4 aces
the chances
of
are a
the
lot
same
better.
spade.
Yep.
That'd be insane.
But I don't really need a whole lot of math to figure that to figure out the math with casinos. I look at the casino, and the more spiffy it looks, the better the food, the drink, and whatnot, the less likely I'm gonna win.
Just go to the slot machine.
Because the money has to come from somewhere, right? Sorry?
We should all go to Capital Casino.
Is there food
Class
that
trip.
bad?
Well, when I go to a casino, it's a definite loss, 100% loss proposition, because I just go to either the arcade or the buffet. It's like I pay this money, I'm gonna get I'm pretty sure I can do Street Fighter and last at least half an hour.
Yeah, another token.
It depends on the other player, but most of the time it can last pretty long. And then at a buffet, I think I know how much I can eat. So those are the things that I usually do if I ever go to a casino. Last time it was 1992.
Some of us weren't even born yet.
Exactly. Yep.
It costs more than that for the buffets.
Hmm?
1992.
Food hopefully would be better though.
Well, that's what they do is they make it family friendly. The kids have something to do. The older people have something to do. So the entire family can stay there for a long time. No, I take it back. The last time I went to a casino was probably 96 or 97. It was a MGM Grand in Las Vegas. It's not one of the local ones. I went there as a software engineer because the casino was using one of our products to collect data in the slot machines.
I think I remember hearing you say this in a previous class.
Yeah. Well, in the previous semester.
Yeah.
Yeah, in the previous semester. Well, this is worth mentioning too because it kind of talks about troubleshooting and what you can do with computer science. So at the time, I was working for a company in Davis called Z World, Z as in the letter Z, and they make embedded controllers, single board computers, like a Raspberry Pi kind of thing, except this is back in the good old days, and they were kind of expensive. And MGM Grand was putting these things into their slot machines, not to control the machines, but to collect statistics. Like how many times it's been played, how many how much money has been paying out, and so on and so forth. And they have a small network, not Ethernet, not Wi-Fi, which is probably what they do, how they do it now. But it was a wired network using RS-485, which is a kind of archaic way of using wired communication. So anyway, the problem was they found that they have a viral issue. Okay, they started off with one machine that was dead, and as they performed the repairs, more machines will die. Okay, and then it becomes a recurring problem because when you fix all these machines over here, then the whole bunch over there would be dying, and they just could not figure out what is going on, and they thought it was a manufacturing defect. So the company sent me and a few other engineers over to MGM Grand to basically to get to the bottom of this whole thing and try to get it fixed, or at least have it explained. So we went there and we went to the basement of MGM Grand, and the basement of MGM Grand is like a city all by itself. They have these electric golf carts everywhere. Okay, I'm not just talking about like on this campus here. Occasionally, you'll see one of those little trucks and whatnot, to haul around stuff, right? But in MGM Grand, it's like a whole city underground, with all these electric golf carts and people and quote-unquote streets and stuff like that. 24/7, man. I mean, you just go down there and there's always something, always some activities. So anyway, we looked at this problem, and we originally thought that it was a issue with electrostatic discharge, okay? Because MGM Grand is in Las Vegas, and in the summer it gets pretty dry, in Las Vegas, which also means you can basically charge up a lot of electrostatic energy just by rubbing on the carpet. You can charge it up, and I tried it myself. On the first day I got there, I was just intentionally dragging my feet on the carpet, and then walked up to a slot machine and zapped it. The arc was half an inch long.
Your
Half an
finger was
inch
probably
long.
numb for a little bit.
Yeah, that hurts. Yeah, that has a little tingling feeling. Yes.
Because it's very thin.
Yes. So that's quite a bit of energy. So we actually brought along a zapping machine. Basically a instrument that is resembling a taser, right? So we use that on our own boards and say, okay, let's see whether we can kill the board by zapping it, right? And we looked at the connection point for the network because that's the point where things happen, and we keep zapping it, and it's like nothing happens. We looked up the specification of the chip. It is supposed to be able to handle electrostatic discharge, like the amount that the human body can hold. So we couldn't quite explain what is going on, and we just spent like 2 days straight. I didn't sleep, and we were just trying different things to look up. Okay, could it be a power surge? Okay, when they switch, because the casinos are required to do a weekly checkup on their backup power supplies. So they have to turn off the main power supply and let the backup kick in just to check, all the generators are working, all the UPSs are working. So we thought a power surge like that could also do a damage to the board, but it wasn't it. And then on the third day, we saw how they surfaced the machines. Okay, so we saw the technician going up. They have like all these special places where people work. People who work there can just pop up from underneath. It's really quite cool. And we saw how they repair the machines. They just open up the case and then they start working on it without first discharging their own electrical energy, electrostatic energy. So that was it. They were zapping their own boards basically. The more repair they do, the more likely they're going to zap a board. And it was still going by the networking wire, but because they thought the other machines that are connected might be damaged, they would open up the other machines and try to check on those machines. The action of checking on the machines actually killed it. And that's why it was viral. That was it. So we just told them, well, you guys got to buy those, $5, anti-static, straps before you work on the machines. Touch on the case to ground yourself first before you work on the inside. That was the end of it. It was interesting. It was an interesting thing. That's the first time I saw the scale of MGM Grand. The first time, it's like, wow, it's like an underground city. When you look at the underground portion. Yep.
How do you keep your static out?
You just ground it, on the on the regular PC. The case itself is grounded. So if you touch the case of a regular PC, you would also discharge your electrostatic energy. Just the case.
So you put your energy in the case, right?
Yeah, just touch the case of a regular PC.
Yeah.
Yeah, that should do it.
Well, how does it do it? Because it's like metal. You're touching the metal, it goes into the metal.
But that metal also connects to the ground of the
With the rubber feet thing.
Of the
power outlet.
Oh, so it goes into the thing in the power outlet. But
Yep.
what if it's unplugged though?
Huh?
What if it's unplugged from the
If it's unplugged, then it doesn't help.
So if it's unplugged.
So you take a screwdriver. So you take a screwdriver. Just make sure it's the ground connection and not one of the other.
Then you're on your own.
Then you can ground yourself. Yeah.
Yeah.
Probably shouldn't try that. Just
Yep.
Try this at home.
Did you find a way to remove the discharge from yourself? Like when you're walking through a casino, is there a way other than touching the machine?
They can do different carpets. One thing they can do is to use carpets that are semi-conductive, which I think they're starting to use now. So basically, there's no way to build up a charge because as soon as you build up some charge, it would just
Take it back out.
discharge it. Yep.
No, but at that time, did you figure out a way? Did you just constantly wear the strap and just go with it?
You can wear straps. There are certain straps that are not connected to anything, and the way it discharges is it has a point, and you discharge it into the air.
Yeah.
Yeah, I like that screensaver. Linux has the best screensavers. It's always entertaining. But you can also wear straps that are not connected to anything, and what they do is they discharge electrostatic energy just into air. And that's what lightning is. It's really just discharging into air. Yep.
Where would I find some?
Huh?
the internet.
You can go to Fry's.
You can find anything on the internet, even if it
Yeah,
doesn't exist.
so they're called anti-static straps. And there are different types. The typical ones, would be the ones that you actually connect to something. There are different ones too. You can also put ones on shoes. And the way it works is, this is conductive. This part here is conductive. So it's basically taking the charge of your body, to touch the ground, so that it's dissipated, to ground.
Yeah. Oh, the reason I ask because I hate that static. It constantly happens. Like in my car.
Yeah.
Mhm.
Like when I
It's all the
touch
time.
the handbrake,
Costco's horrible on static.
I get a little shock. So that's what I was wondering when you said that there's straps that dissipate
Cook my
that
sister.
static into
I
the
hate
air.
when you go grocery shopping.
Yeah, Costco.
Yes,
Costco.
Yeah, Costco particularly has that problem. I think it has to do with how the kind of polymer that they put on the ground to protect the cement. Yep.
Yeah.
Yep.
Or wax.
Most shopping carts, if you look at the bottom, have a little metal
Yep.
thing that hangs down.
Is there any way to
heard that one.
with the charge, that just kind of spreads it out, right? Neutralizes it. Can you store it somewhere? So you can I don't know, use the electricity later.
Okay, so there
Charge it
you.
up into a battery.
Okay, so there you have it. Wireless or dissipative wrist straps are available, which claim to protect against ESD without needing a ground wire by air ionization or coronal discharge. So these are widely regarded as ineffective. Fraudulent. Okay, so if you're working on your own computer, always wear things that are connected, wired.
Or just touch the case real quick.
Well, touch a case that is connected.
Specific.
Yeah, it has to be connected. It has to be a metallic case and it has to be connected.
Or have a lightning rod just right next to it into the ground, so you can just grab the lightning rod.
Yep. That'll do it. Yeah, to understand electrostatic energy, you can watch Mythbusters. They did quite a few interesting episodes.
That's true.
Yep. They combine electrostatic energy with water. I think there was one episode they were, spraying water on something and then do a discharge through the path of the water. Yep.
It has to be space.
All right.
Yeah, it's like peeing on an electric fence.
It doesn't go and jump like at you. It's usually inconsistencies in the flow.
Yep.
According to them. According to
I did it
them.
one time. I'll never
All
do it
right, so
again.
back to recursion, back to factorial. What are the chances we can get that? Well,
Let's try.
All right, so back to recursion. So why is this? Why is factorial? Well, we know why factorial is useful. Okay, it's for probabilities and a few other type of things. The question now is, how does it relate to subroutines or recursion, which is the main topic today? Okay. Well, if you look at let's say 5 factorial, you can write 5 factorial as 5 times 4 times 3 times 2 times 1. Kind of boring. But when you regroup things, you can regroup things a little bit because of the associative property of multiplication. You can group the other 4 items on one side and then 5 as an individual item. What is 4 times 3 times 2 times 1? Not the value of it, but what is another way to look at it?
4 factorial.
It's 4 factorial. Very good. Okay, so now 5 factorial can be expressed as 5 times 4, the factorial of 4. Okay. So if you look at 4 factorial, it doesn't take much time to realize that 4 factorial is 4 times 3, the factorial of 3, and so on. So you can keep this going until you get to 1 factorial. What is 1 factorial? Well, 1 factorial is 1 times 0 factorial. By definition, it is. Okay? And then 0 factorial is by definition 1. It does not go any further. Okay? The reason of 0 factorial being 1 is there's only one way to arrange nothing.
Yeah.
Interesting.
It is interesting.
Okay?
Never interesting.
But that's the definition of 0 factorial. Okay? But the point is, it is recursive. In other words, the operator, the definition of the operator itself, relies on itself. Okay? The very same operator that you're trying to define can define itself up to a certain point. Because at a certain point, it becomes what we call the base case, and in the case of the base case, it is no longer recursive, which means 0 factorial is just 1. Okay? By definition, you cannot go any further. Are there any questions about the definition of recursion or recursive definitions? We encounter recursive definitions in computer science a lot. A lot of names are recursive. We can look up wine. Okay, wine in Linux land is wine. Let's see, is not an emulator. Okay, that's the definition of wine. The program. It is wine is not an emulator. So what is wine again? Wine is not an emulator. What is wine? Wine is not an emulator. So you never really quite figure out what wine really is, but you know what it is at the same time. Okay. We also have lame. L-A-M-E. Lame stands for lame. Ain't an MP3 encoder. Or the most one of the more original ones is GNU. GNU is not Unix. That really is what GNU is. It's not Linux. It's not Unix. Okay, so we have all these tricky things about recursion. But we also use recursion on a daily basis, but without knowing it, because that detail was actually well hidden from everyone. It's when you delete a folder. Okay. Now, when you try to delete a folder using a command line program like del in DOS or RM in Linux, it won't let you delete a folder unless the folder is empty. It has nothing in it. Okay. So how do you make sure that folder is empty if it has subfolders? Well, you go to a subfolder and then look at it and go like, can I delete you? No, I have got subfolders or subfolders. So you go to the subfolders and then you do the same thing. And that's recursive too, because the recursive action is I will check whether this folder is empty. If not, I will remove all items first. But what if one item is a folder? You go into that folder and you do the same thing. You keep doing this until you get to a folder that has no subfolder. So you can just delete all the files, go back up one level. This folder is now empty. You can delete it. Okay. So we do all these things, already that are recursive. It's just that with computers today, you can just highlight a folder and just press the delete key, and it will do the recursive delete for you without asking you, oh, do you want to do it recursively? No, it's by default already recursively. All right. So are there any questions about recursion? Okay, no questions. For some of you, you may not see recursion a whole lot more after this class, if your major is not in computer science. But if you're in computer science, recursion is going to be one of the very interesting and useful concepts, because we have a lot of data structures or ways to arrange things that are also recursive. How many people know what is a fractal thing, fractal graphics? Okay, it looks kind of interesting, right? And what is fractal graphics? Let's take a look at a picture of a fractal pattern.
It's a repeating pattern.
Yep, it's a repeating pattern, and it gets smaller and smaller. Okay. So if we look at images of fractal patterns, this is a good one, the tree one. And that's a fractal pattern. Okay, because a branch separates into smaller branches, separates into smaller branches, separates into smaller branches. Doesn't that resemble an actual tree? That you have a main trunk into big branches, and then you take one big branch, it separates into smaller branches, and of course, the recursion ends, with what? Leaves, right? Exactly, because a leaf, cannot branch out anymore. That becomes the final thing. Okay. So we do find recursive stuff, on a daily basis as well. But in computer science, it's mostly a way to analyze something, kind of using very interesting techniques. All right. So the next thing we want to do, now that we know what recursion is and it can be defined recursively, let's complete the definition of recursion in this case. So n factorial is 1 if and only if n is 0. But n factorial can be defined as n times the factorial of n minus 1 if and only if n is greater than 0. So you can look at the definition of factorial like this. Is that making any sense? If I ask you to compute 0 factorial, then by definition it is 1. But for anything other than 0, for any positive integer, then the factorial of n can be defined as n times the factorial of n minus 1. Is that okay? Let's see if we can capture that logic using an algorithm, because that's what we are here for, is to write algorithms to solve problems. So this is what we want to implement, only this part, and we'll use an algorithm to do it. So we'll hide a portion of this so we can actually see the definition on the side here. And we'll define a subroutine called factorial. We'll worry about the line numbers and stuff like that later. Okay. So it looks like whether it is 1 or the factorial of n minus 1 times n depends on what n is. Okay, so we'll go ahead and use a conditional statement for that. So we'll basically say if n is 0, we do it in one particular way, and if n is greater than 0, we'll do it in some other way. So we'll say if n is greater than 0, then we'll do it in one particular way, and the else we'll do it in some other way. Okay. So the else is quite simple. Yep, go ahead.
What if n was 1? Wouldn't that be the same as if n was 0?
Correct. It is. But by definition, you have 0 factorial equal to 1. But 1 factorial is 1 as well, because there's only one way to arrange one thing. Okay, so if n is 0, then we say the result is 1. Okay, that's the end result of the whole thing. But if n is greater than 0, then what we can do is to do the following. We can, okay, there are several things that we need to do. First of all, we have to say, okay, let's consider n minus 1 first. And then we invoke factorial. Because invoking factorial is supposed to find me the factorial of n, which is now 1 less than before. And the result is supposed to be in R. So once I have that result in R, then I can say, well, you know what? I know the factorial of n minus 1 at this point, so it is time to recompute the actual factorial of this particular n. So before we do that, well, there are several ways to do it. The first one is let's reverse n back to where it was before, and then we can compute the actual factorial. So let's insert a row here. And then we can say, the result of this is whatever result I got from the factorial on line 4, and then multiply that by n, which is what I'm supposed to solve. And on sub, there are really several ways to write this, so this is just one of those many ways. We'll highlight a few lines. There's one in end. It's really clumsy because we are lacking a few concepts that will make it very nice, look a lot nicer. All right, so outside of the subroutine, the only thing I have to do is to specify n, which is the number that I want to find a factorial for. So let's just say that we want to find a factorial of 3, and then we say invoke factorial. All right, so let's see if this algorithm works the way it's supposed to, and if so, how does it work? Now, what you need to do when we talk about this topic is to relate what I'm doing here as far as the invocation is concerned on line 4, particularly, and what we do at the end of a subroutine, to see if we are still doing exactly the same thing as what we talked about last Thursday. Okay? So we have comments because we have one condition on line 2 to evaluate. We have line number, and then we only have 2 variables this time. We have variable n, and then we have variable r. Neither needs to have any assumption because I'm going to initialize each one inside the algorithm. And here's the interesting part. I can see that we are initializing n directly on line 11, not a problem. But what about r? R is initialized here, but what about using r when we're on line 6? How can we be sure that by the time we get to line 6 that r has a particular value? That's the question. We'll answer the question as we go through the trace. So we start execution on line 11, which is the first line outside of the definition of a subroutine. And it doesn't do anything too exciting. N gets a value of 3 to begin with. And then we move on to line 12. Line 12 is the invocation of a subroutine. It has got 2 things to do. The first one is to allocate the leftmost available column and then label it return line number. And then we use that column to remember where we are supposed to go back to. Since we are on line 12 right now, when this subroutine is done, where am I supposed to go back to? Post. Okay, that's very good. And then the second thing invoke is supposed to do is to continue execution at the beginning of the subroutine that we're invoking. Which line is the beginning of the subroutine factorial?
2.
Line 2, very good. All right, so now we're on line 2. We evaluate the condition on line 2, n is greater than 0. N is 3, 3 is greater than 0 is true. So we move on to line 3. Line 3 doesn't do anything too exciting. It just decrements the value of n by 1, and then we get to line 4. Line 4 is the invocation of factorial. So we do the same thing as last time when we invoke factorial. So we have to allocate the leftmost available column, which is column F at this point, label it return line number. And where am I supposed to continue execution when the second invocation of factorial is done?
5.
Line 5, because line 5 is logically following line 4. Okay. And what is the second thing we have to do when we invoke a subroutine? To continue execution at the beginning of the subroutine. But tag, we are already in the middle of the subroutine. Are we really quite sure that we want to start from the beginning? Yes. Okay. Every invocation starts from the very beginning of the subroutine that you're invoking. Whether you're in the very same subroutine to begin with does not matter. Okay, so in this case, line 4 is clearly in the subroutine that we're invoking. It doesn't matter. Okay, every time you invoke, you continue execution from the very beginning of the subroutine that you're invoking. So we are now back to line 2. Line 2 doesn't do anything too exciting. It's just testing n. N is 2. 2 is greater than 0 is true. So we go to line 3. Line 3 is going to decrement the value of n, so it becomes 1. And then we go to line 4. Line 4 is invoking factorial again, and by this time you should probably find that it's kind of boring. Allocate the leftmost available column, label it return line number. Remember the line that is logically following the invoke statement itself, and then we continue execution at the beginning of the subroutine that we're invoking, which is line 2 in this case. N is 1, 1 is greater than 0, so n is greater than 0 is true. Yep.
A little bit off topic.
Go ahead.
Did you auto resize that column? What did you press?
When I auto resize, I highlight the column first, and then I wait until my cursor becomes a double-sided arrow. At this point, I can either drag it to manually resize the column, or I can double-click it.
Okay.
Double-click will auto resize it.
How do you resize all of them?
Same thing. You basically highlight all the columns that you want to auto resize. Go to any border, and then just double-click it.
Don't you have to use control?
Nope, just double-click.
No, to highlight.
Oh, to highlight?
Yeah.
You can do a shift click if they're contiguous,
shift.
or if they're not contiguous, then you can use control click. Then you can select only specific ones, and then the same thing, double click when your mouse cursor becomes a double-sided arrow, then you can resize all of those at the same time. Sure. All right, so we're back to line 2, and n has a value of 1 at this point. 1 is greater than 0 is true. We go to line 3. We now decrement it to 0, and then we continue on to line 4. We have to go invoke one more time, okay? Because to us, we are already understanding, oh, okay, n is not greater than 0 anymore. We should stop now. But as far as the algorithm is concerned, it still has to follow the logic that is specified. So at this point, we are still going on to line 4 and still invoking factorial. So factorial will invoke factorial of line 4. It's going to do the same thing as last time. Allocate the leftmost available column. Label it return line number. Remember where we're supposed to come back to, which is line 5. Sorry?
Yeah.
And then we continue execution from the beginning of the subroutine that we're invoking, which is line 2. Okay, we're back to line 2. We're evaluating n is greater than 0, but this time n is greater than 0 is false because n has a value of 0. 0 is greater than 0 is false. So we continue execution in the else, which is line 8, and line 8 at this point is going to initialize r with a value of 1. Are we doing okay so far with this trace? We're running out of space, vertically. So what I will do is to do this trick here. There's a little bar here, and when you drag this bar, it will separate the screen here vertically into 2 halves. And now that it has separated into 2 halves, I can scroll vertically with one part without impacting the other part. But if I scroll horizontally, both will basically synchronize and scroll at the same time. This is a really useful feature when you are using a low resolution screen like I am, and you're running out of columns. Okay, so you can actually still kind of scroll things around and look at 2 different parts of the same spreadsheet at the same time. All right, so we are on line 8. Line 8 is initializing r to a value of 1, and then we can get out of the conditional statement. Continuing on to line. We just executed line 8, which is the only statement of the else branch of the conditional statement. So where are we going to go next?
And define sub.
And define sub. Okay, and define sub is where we go to, because we have to get to the end of the subroutine to determine where we are supposed to go. So on line 10, now we got 2 things to do. When you're on end define sub, the first thing you have to do is to locate the rightmost active return line number column. In this case, the rightmost active return line number column is column H. And column H is telling me continue execution on line 5. So I'm looking at this 5 here and say, okay, I'll make a note to continue execution on line 5. After I make that note, I have just made use of column H. So column H is not useful anymore, so I'm going to deallocate it. So column H is now I use the strikeout font effect to basically say I don't need this column anymore. It is now deallocated. At that point, I can now continue execution on line 5. Line 5 is right here. It's just n gets n plus 1. So we are going back from 0 to 1, and then we move on to line 6. Line 6 is multiplying r and n, and then storing the result back into r. R has a value of 1, n has a value of 1. 1 times 1 is 1. So on line 6, we're going to store that back into r, which has a quote-unquote new value of 1. After line 6 is the last line of the then branch of the conditional statement. So now we get out of the conditional statement, we end up on line 10 again. Line 10 is going to do exactly what we did last time. We have to locate the rightmost active return line number. Which column is the rightmost active return line number?
G.
Column G, and where am I supposed to go next? Line 5, right? So we'll first make a note that we have to continue execution on line 5, and then we have no use of column G anymore, so we'll use the same notation on line 10 when we execute line 10 to mean that column G is now deallocated. Now we're back to line 5. Line 5 is adding 1 to n goes from 1 back to 2, and then we move on to line 6. Line 6 multiplies r and n together and then store the result back into r. N has a value of 2, r has a value of 1, 2 times 1 is 2, and then we store that into r, which is column D. And then we move on to line 10, because line 6 is the last line of the then branch of the conditional statement. On line 10, we do the same thing. We locate the rightmost active return line number. It is not column G, it is now column F. Column F tells me to continue execution on line 5. That's where we're going to go. Line 5 is going to add 1 to n goes from 2 to 3.
You didn't deallocate F.
Oh, okay, that's right. Thank you. So we have to deallocate it here. Thank you. So back to line 5, we are adding 1 to n goes from 2 to 3, and then on line 6, we multiply r and n, which is 3 and 2. The product is 6, we store that into r, and then we get out of the conditional statement onto line 10. Same thing happens on line 10, we have to locate the rightmost active return line number, which is column E. Column E tells me to continue execution at post. We'll make a note of that. And then we have no use of that column anymore, so column E is going to be deallocated at this point. And then we continue execution at post, which means we're all done. Are there any questions about this trace? Any questions about how we dynamically allocate columns, make use of those columns, and then when we're done using those columns, we clean up and say, okay, this column is not needed anymore. No questions? Yep.
Question. How do you want us to do the strike through thing, or is there another way we can?
You can do the strike through thing, or use some other way to indicate that they are deallocated. But you do need a notation, to tell me that okay, this column at this point is deallocated. Yep.
Can you just put like post instead of doing the right through, just put post?
It's not post. Okay, post does not work because we only have one post at the very end of the entire trace. But strike through is not that hard. I mean, you just right click, go to font effect, and then just select, strike through. We're talking about, maybe 2 seconds, right?
Too long. Us youth nowadays. Go.
Exactly.
Yeah. Oh yeah.
Yep.
You don't have to get efficiency. You don't have to format it. You just copy and paste it.
Maybe we could write an algorithm that
Yeah,
would
keep the
do it
strike.
automatically.
Yeah. Yeah. When you copy the content of a cell, it copies the formatting of that cell as well. All right. Well, this one looks okay, but if you look at the general shape of the recursion, okay, let me just kind of combine the two panes into one, and just to kind of zoom out. It's going out and then go back in again. So it's not that interesting, okay? Let's look at Fibonacci numbers. Another type of recursive definition, Fibonacci. So we look it up, Fibonacci. Here we go. Yep.
Roll sheet.
Roll sheet. Thank you. Thanks for the reminder. You can pass it. And I can pass you the one that, just cross out the cross that I put on it. Okay. All right. Fibonacci numbers. What is it used? Well, let me first ask you this. Which movie refers to Fibonacci numbers? There are multiple movies, just name them. Yep. The Da Vinci Code, that's definitely one of the movies that refer to Fibonacci numbers. And how was it used in that movie?
I just remember Fibonacci from Prison Break.
From what?
Prison Break.
Prison Break?
Yeah,
Okay.
show.
The Da Vinci Code. Okay. And we want to look up Wikipedia because we want to look up, Fibonacci number. Okay.
Nothing.
Okay, so here's how it was used. The note also includes a Fibonacci sequence left out of order as a code. And as a code, I barely remember how it was used. It was a part of a password, if I remember correctly. It was either that or it was telling people how to do certain things. I cannot remember, but it was based on the sequence of Fibonacci numbers.
Well, during that sequence, that's when he was laid down and he was doing like the Eternal Man pose. He had like the blood ring around him, and like someone was doing like a ritual or something.
Right. But I cannot remember why the Fibonacci sequence was there to begin with, and why it was out of
The
sequence.
only code they had was that little box, and you put Apple on it.
I'll watch it tonight and let you know.
And,
Okay, that would be your homework, right? This is your homework before Thursday. You can actually tell, other people and say, "I'm doing my homework. Don't disturb my movie." But I only need that part that talks about the Fibonacci.
It's YouTube.
YouTube, yep.
YouTube has all the answers, even if they're not right.
Between
Especially-
YouTube and Stack Overflow, you have all the numbers, all the answers of everything. Okay. All right, but this is how it's defined. Okay, this is recursive again. So in general, the f of n is f of n minus 1 plus f of n minus 2. That's in general. Until we get to f of n, by definition is 1. F of 2 by definition is 1. F of 0 is by definition 0, and so on. Okay, so you can choose one or the other as a base case. So you can either define f of 1 and f of 2 as your base case, or you can define f of 0 and f of 1 as a base case. So in this class, I'm going to use f of 2 and f of 1 as a base case, just so that we don't have to go through that one extra recursion to get things done. Okay, so we're going to look at this code here, look at this definition, and then we ask, how do we write an algorithm to do that? Now we'll go ahead and try to define the subroutine. We'll just call this subroutine F for Fibonacci, and then we have several cases to look out for. So in other words, when you look at a recursive definition, you have to spot when you can stop the recursion. In other words, what numbers have fixed answers? Okay, so you look for those things first. Okay, one way to look at it is to look for those things first. So in this case, we say if n equals to 1, then we know for sure that the result is going to be 1 by definition. I'm using this definition here. Else if n equals to 2, then the result is also 1. Now, if you want to, you can combine the first and the second test case, because in both cases, the result is 1. So one way to do it is to say if n equals 1 or n equals 2, then R gets 1. Okay, but I'm separating these into two branches just to make it very clear and also follow the logic of the definition. Now, for all other cases, which is handled by the else, we have to use the much more general definition. So what we need to do in this case is to decrease n by 1 first, okay? Invoke the Fibonacci number subroutine. And when it comes back, r has a particular value. But this r is kind of important. I want to kind of save it first because I have to do another calculation using r as well. So I better stash this away using another variable. Let's just use x to store this r just for the time being. And then I will invoke. This will be interesting. Well, because okay, this will be. It will be clear why this is not going to work because I only have one x here, so the recursive definition will also trash this x as I try to compute the Fibonacci of a smaller number. So I may not have the necessary constructs to get this done at this point. Let me think about this a little bit because I have to utilize the result right away before I make use of it again. I don't think I can get it done. But I can, I don't think I can get it done because I'm lacking a particular concept that is necessary to get this done. So I'm gonna leave it the way it is right now because it cannot be done. The concept that I'm lacking right now is called a local variable, and we haven't talked about local variables yet, and that's why I cannot do this. I can finish the algorithm, but we can trace it and see why it is not working. Okay. So I'm going to save the result of the first Fibonacci number into x, and then what I need to do is to figure out what is the Fibonacci number of n minus 2. So that means at this point I have to subtract 1 again from n, so it becomes 2 less than what it used to be, and then invoke f again. Now, when f returns this time, r would be the Fibonacci number of n minus 2. So now the end result becomes what the number is, and then plus x, which is the Fibonacci number of n minus 1. And that becomes the entire else case and define sub. But I can almost guarantee you that this is not going to work in general. It will work for smaller numbers, but it won't work for larger numbers. But it is helpful to look at this and figure out why it's not working too. This is the first time I try to do Fibonacci without using local variables. And right away, I kind of know that it's not going to work. But we'll take a look at C and try to see why it is not going to work. Okay.
What do you mean by local variables?
Well, it's one of the concepts, in subroutines. A local variable, and this is like fast forwarding into a topic that we will have to cover. A local variable has two locality. Why it's called local? The first reason why it's called local is because it's only accessible within the subroutine that you're defining. Okay. But the second reason why it's also called local is because each invocation has its own copy. And right now we don't have anything that is on a per invocation basis other than a return line number. So this one is for sure not going to work because of that. Yep.
Is this just trying to trace it, or is this trying to find a certain term in Fibonacci sequence, or what's this trying to do?
This is trying to compute the Fibonacci sequence number of n. That's what the subroutine is trying to do.
N hasn't been established yet for an initialize.
So you're trying to find a specific term then?
Right.
Gotcha.
Yeah. But it's not going to work because because x is a global variable. There's only one of it. So when I do the recursion, it will trash this x with another result, and there's no way to recover after that. Okay. So we'll take a look at how this is going to not work. Okay, it's going to. So we'll start with and when n is a small number, it's going to work out. Okay, so I need at least 2 levels of recursion for this to not to work. So that means n cannot be 1, n cannot be 2. If n is, oh, okay, I forgot one indentation level here. If n is 3, then I will call this one once, and then it will come back, save it, and then do it again. That's still not going to work. That's still not. That will still not, break the algorithm. So n has to start with 4 in order for the algorithm to not work correctly. So now I invoke f, and we'll take a look at what happens now. Okay. Where's my other window? Right here. All right. So we do have one column for comments because we have a conditional statement. And then we have my number. And then we have r, x, and n as our variables. N is going to be initialized. R is going to be initialized. And x is going to be initialized in the algorithm itself. So as a precondition, I don't have to give you anything. No, I don't have to give you any known values in each one of these variables. We start execution on the first line that is outside of the definition of the subroutine, which is on line 15. It puts a value of 4 into n, and then we continue on to line 16. Line 16 is invoke f. It first allocates the leftmost available column. Remember where we are supposed to go back to, and then continue execution in the subroutine that we are invoking, starting from the beginning, line 2. N equals 1 is false. We go to the second case, the second branch, which is comparing n to 2. It is also false, so now we have to go to the else branch on line 7. Line 7 starts with subtracting 1 from n goes from 4 to 3, and then we go to line 8. Line 8 is invoking f again. We allocate the return line number from the leftmost available column. When we come back, we should continue execution on line 9 because the invocation is on line 8 itself. And then we continue execution from the beginning of the invoked subroutine, which is line 2. N equals 1 is false. We move on to line 4. N equals 2 is also false. Then we move on to line 7. Line 7 is going to decrease n by 1, so it becomes 2. And then we move on to line 8. We invoke f again. Allocate the leftmost available column and indicate where we are supposed to go back to, which is line 9. Continue execution at the beginning of the subroutine that we're invoking, which is on line 2. N equals 1 is false. Move on to line 4. N equals 2 is true.
Wrong cell.
Oh, I shifted everything.
No. N equals 2 is true was in the wrong cell.
N equals 2 is true.
In the wrong cell.
Oh, okay, I see. There we go. Thank you. So this is true, so we move on to line 5. Line 5, do you guys have a question? Nope. Okay. On line 5, we are going to say result is 1. And then we get out of the entire conditional statement because this is a multi-branch one. Once we're done with one branch, we get out of the entire thing. So then we move on to line 14, which is the end of the subroutine. We look up the rightmost active return line number. It tells us we have to continue execution on line 9. And then we have no use of this cell, this column anymore. Go to strike through, and now we're on line 9. Now this is the first time we get back onto line 9. There will be a second time. So when we get back onto line 9, we try to save the value of r into x. And let's take a look at which column is x here. Just by x is column E. So we copy r to x. So x column E is now having the same value as r. And then we move on to line 10. On line 10, we subtract 1 more from n. So n goes from 2 to 1. And then on line 11, we invoke f again. We allocate the leftmost available column. Which column is the leftmost available right now?
H.
column H, because we just deallocated that column, so this becomes again available. So we are reallocating column H to store our return line number. The invoke is on line 11, so the return line number is going to be line 12. And then we go all the way to the beginning of the subroutine again on line 2. N equals 1 is true to begin with. Go to line 3, R gets a value of 1, and then we have nothing to do with the conditional statement anymore. We get out of the entire conditional statement. We get to line 14. We look up the rightmost return line number, which is once again column H. It tells us to continue execution on line 12. And then we have no use of column H anymore. So this is the second time we deallocate column H. Are there any questions about the allocation and deallocation of column H? Nope. Okay. So we're back to line 12. Line 12 is adding R and X together. R has a value of 1, X has a value of 1, and then we store the sum, which is 2, into R. Okay. Oops. There. And then once we're done with line 12, we get to the end of a subroutine on line 14. Line 14 is the end. It looks up the rightmost active return line number, which is column G. Column G tells us we have to continue execution on line 9. So now we're back onto line 9. Line 9 is going to copy R to X again. So R is going to copy it to X, which is here.
You didn't allocate 14.
Oh, you're right. So we have to deallocate this column because once we execute line 14, we have to indicate column G is now deallocated. Thank you. Back to line 9, we copy the value of R to X over here. So now X has a value of 2. And then we move on to line 10. N gets N minus 1.
0.
Yep, it's not going to work because I forgot to add the value of N back to before doing the return. There's supposed to be a line here. I forgot about this because I have to restore the value of N first before I return all the way back out. So I forgot about this line here. We'll call this 12.5.
Or 13.
Rounded.
I'll do this, or maybe that.
Okay, so it's between these two lines, so we have to add one more line here. So when we execute line 12.5, N goes from 1 back to 3. So now when that would not impact getting to line 14. It would not impact going back to line 9, but it does impact when we get to line 10. Because when we get back to line 10, N gets M minus 1. So 3 becomes 2, and then we go to line 11, we invoke F again. So this time we reallocate column G, because that's our leftmost available column, and we use it as a return line number. And the return line number this time is, the invocation is on line 11, so we get back onto line 12. And then we go from line 11 all the way to the beginning of the subroutine, which is on line 2. N equals 1 is false. We go to line 4. N equals 2 is true. Then we go to line 5. R gets a value of 1. Get out of the entire conditional statement. Continue on to line 14. Line 14 is going to look up the rightmost active return line number, which tells us to continue execution on line 12. And then we have no use of column G anymore. So once again, we deallocate column G, and now we're on line 12. Line 12 is adding R and X again. R has a value of 1, X has a value of 2. It is now 3. Okay, so right now we want to add 2 back into N, so we have line 12.5 at this point. N is now 4, and this is the question. Is the Fibonacci sequence of 4, is that value 3?
Right.
Let's go back. Okay, this is saying the Fibonacci sequence of 3 has a result of 4. Okay? Nope, take it back. The other way around. F4 is 3. Okay, that's what they say. F of 4 is 3.
Did we finish? I thought there was one more return line we had to do.
F of 4, sorry?
Wasn't there one more return line we had to do?
Yeah, there's one more, but I can check now to see if it's
Oh.
correct. So up to this point, it is still correct. Because, you know, this is 1, 2, 3, 4. So it is the correct number for 4. And then after 12.5, let me get back to the algorithm. After 12.5, we get out of the conditional statement. We end up on line 14. Line 14 is a return, or at the end of a subroutine. This time column F is going to be used. So it goes to post, make a note, and copy and paste it. So it did calculate the number correctly because F of 4 has a result of 3. I didn't break it. I thought I would break it, but I did not. But when you look at the columns or how we use the columns in this particular case, you know, we are running out of time. It is a little bit different from last time because it has to do with allocating and then deallocating and then reallocate and then deallocate and then reallocate over here again.
Oh God.
Okay, so this is actually why recursion is useful, because to do this without recursion is going to be a little bit harder. I'll see you guys on Thursday. Oh, by the way, we have a practice test on Thursday, so that on the Thursday right after break, we'll have the second exam.